just started recording. Please go ahead, Denis or Gunnar.
Okay. Give me just 1 second.
And while they get set up, please introduce yourselves in the chat. And if you'd like to work on use cases documents with us, please indicate in the chat. We're collecting graph use cases.
Here's our presentation on graph databases and outlier detection and dynamic recommender systems. I'm Denis Vrdoljak, and with me is Gunnar Kleemann.
Hi. We're going to be switching off back and forth throughout the talk. Just kind of how we.
Here's a quick roadmap of what we're going to talk about. So first, a little bit of an intro. Gunnar and I met at UC Berkeley, and we started working on a project, ended up doing our capstone together for our master's. And as we were developing that, eventually we started Berkeley Data Science Groups to try to bring ideas and projects from Berkeley to market and to create a vehicle for that. So that's where Berkeley Data Science Group came from. And here's our contact info. We'll share it at the end as well. I'm on one of the data science teams in the CISCO marketing BU, and Gunnar is a full-time instructor at Berkeley. After Berkeley, we both came back and taught, excuse me. After we graduated from Berkeley, we both came back and taught Python for Berkeley. For me, just a couple of the summer sessions, and Gunnar came on as a full-time data science instructor for the School of Information. So if you're here, you guys might have the question, why graphs, why graph databases, what are graph databases, and when do you use them? And this question comes up a lot. So the data that's stored in a graph database is stored in tables and rows and columns, just like a relational database. The big difference is in the implementations is that a graph database is optimized for graph traversal, whereas a traditional relational database is optimized for data retrieval. So that actually makes graph databases a little bit slow when you're retrieving data, but orders of magnitude faster when you're traversing a graph. And the way that the implementation works, a first-class citizen in a graph database is considered a relationship between objects, whereas in a relational database, the first-class citizen is an entity, a thing with data about it. And so a little bit of background. Graph theory really started with Leonhard Euler in the 1700s with the 7 bridges of KONIGSBERG problem. He laid down the groundwork for what eventually became modern-day graph theory. And that's also evolved into social network analysis, and the literal networking sense, like what we do at CISCO, and a lot of other fields and applications. Really, whenever you're working with data about interactions between objects or how they interact with the world around them, those representations can be dealt with in a graph, and graph algorithms are really good for finding out some of the intelligence that's buried in the data. So with the 7 bridges of KONIGSBERG, Euler basically turned a problem with a couple of land masses, and the question, can you cross every bridge only exactly once? And visit those different areas of the city. And he turned it into a graph problem and ultimately proved that no, you couldn't. But in turning it into a graph problem, that laid down the foundation of nodes and edges and traversing a graph. And some of the applications of graphs are...
Your video off so we can get more bandwidth. It's coming out patchy, and if you shut your video off, it's going to be better.
Yeah.
Sorry to interrupt.
Kill them. There we go. So some of the applications of graph databases, recommender systems comes up often. And in a traditional recommender system like Amazon's recommender system, where it's dishing out tens of thousands of recommendations every hour, that's something that you would want to do at scale with a traditional recommender system. With a graph database, you can create a recommender system to really explore the data and to dig out some of the rules and relationships between the different nodes. And so with a graph, you can really do a good job with subsetting the graph and get localized recommendations or context-based recommendations. But if you're going to deploy it into production, you will want to do it with a traditional recommender system, because extracting the information, which is the recommendation, will be a lot faster with a relational database as opposed to with a graph, where the traversals are fast, but extracting the data is a bit slower. And we're going to talk about a couple of traditional examples and then dive into some of the work that we've done in graphs.
Might it be better if Gunnar shares the screen? Because you're still quite patchy.
Yeah, let me try. I may or may not. I'm at home too, so it's
okay.
Potentially. Is this updating?
Looks much better now.
Okay. I think we're here, right? Or is it forward?
Yeah, next slide.
Next. Okay.
So some of the some of the common applications are social network analysis. So traditional examples like Facebook or LinkedIn data, and identifying what the communities are and how communities interact with each other. Maps and GPS are another classical example, where it's basically a shortest distance calculation in a graph with weighted edges. AI algorithms and search engine algorithms, and also machine reasoning, with being able to make deductions that are not in the data based on other rules that are in the data already. Next slide. So some of the places where graph theory has been applied, here's a few of them. The 9/11 terrorist network, after the fact, unfortunately, there was a graph analysis done that really highlighted the connections between all the individuals involved, and using graph metrics really highlighted which people were influential and which ones were kind of calling the shots. Unfortunately, after the fact, the London phone case study of inbound and outbound phone calls in London and where they were going to. And one of the conclusions that they found was that areas that had more calls outside of their locale were correlated with more affluent neighborhoods. So you get into the question of cause or effect there, but they found a correlation between the proportion of long distance phone calls versus how affluent the neighborhood was. An analysis of the Enron emails showed who was in charge and who was really calling the shots, in addition to who had the official title with all the people involved. And another one that is one of our future projects is looking at the Panama Papers and all of the data that's in there. Next slide. So we're going to go over a couple of examples of our work. Next slide. one of the first things that we're going to show you is a keyword recommender system, where an application of this would be if a recruiter is trying to figure out which keywords to search for to narrow down the applicant pool. This would provide recommendations on related keywords. So this is a example of a recommender system. Next slide. So in the typical job requisition, you have the title, the company information, the geography, basically the metadata. And so that metadata you can use to subset the graph, and the information, the knowledge that we really need for the recommender system is in the relationships between the skills. Next slide. And so here's a example of a couple of companies and cities and job titles and some of the skills that come up in those job titles. Gunnar's going to walk us through a couple of the features here.
Okay. Can you all hear me?
Yeah.
Yes, it's great.
All right. So you might focus on a specific skill. Let's say you have a skill set that's fairly focused on DNA analysis. If you go back to the graph, you can see that this skill is here, and you might say, okay, well, where will I have the most traction from my skill? And in this is just obviously a toy example, but it reflects the real pattern where San Francisco has the lion's share of bioinformatics jobs, and DNA analysis would be better used probably in San Francisco than Austin, for example, where there's a small number of bioinformatics companies. You can traverse the other way and say, okay, if I want to live in Austin, is there a skill that I have to have? And in this schema, we see that everybody's asking for somebody who knows SQL. So we can filter by Austin or another place and say, okay, well, these other skills are less absolutely required, but SQL is required by both of these companies for database manager. Another application would be if you have a specific skill set and you want to know if there's anything missing. Like for a bioinformatics job, you might need R and data and DNA analysis, but you may not know that you also need Python. So if all job ads mention Python in a cluster with this other two skills, it'd be important to study up on Python to get those bioinformatics jobs.
So we built a API to analyze some of these relationships, to really simply put in a query, what's the skill that we're looking for, and then the metadata. For this example, we just use the city as to subset the data, and then have it return the related skills. So we did some NLP to extract the relationships between the features as related skills or skills that go together. And here you can see some of the differences between New York and Silicon Valley for Python. In Silicon Valley, you see that Unix comes up a lot with Python as being related and the job requisitions, whereas in New York, you see SQL and R coming up a lot more. And that really speaks to the stereotype, but also an actual, based on the companies that are in each area, where in Silicon Valley, there's a lot more emphasis on consumer-facing products, whereas New York has a lot of the large financial institutions where they do a lot more statistical analysis as opposed to consumer-facing applications. Next slide. So we did an analysis on this and pulled data from San Francisco and New York. I grew up in Silicon Valley. Gunnar grew up in New York. And so we wanted to see who has better data scientists based on the job requisitions for each region. And so we pulled about 40,000 jobs from each one and did the NLP to turn them into a graph and then analyze the graph with the API. Next slide. So here you can see a couple of examples. In New York, you see a lot more emphasis on financial because of all the financial institutions there. Whereas in Silicon Valley, you see a lot more emphasis on Google technologies. Next slide. When you look at market versus marketing, this really jumps out, where in Silicon Valley, there was a lot more mentions of marketing in the context of data science jobs, whereas in New York, the specific word market was mentioned a lot more, where that would apply more to financial markets. Next slide. And here's a couple more. Interestingly enough, in New York, there was the mention of the degree requirements in job requisitions, whereas in Silicon Valley, there's a lot more mention of experience and the environment. Next slide. And here's some of the other ones that came up. You see analysis and analysts coming up a lot more in New York, where the emphasis would be on really optimizing large institutions' systems, whereas you see application and engineering in Silicon Valley with a lot more of the consumer-facing products. Next slide. And now we're going to take a look at the first project that we did and how we've developed it since starting.
Do you want to take a quick question? Somebody asked if you're dealing with real-time data or stored data.
This is all stored data. So we do collect the data and then do the analysis as a separate step. We weren't dealing with real-time data because if we pull with job postings, the real-time data wouldn't have as much meaning in that case. But also, if we did the analysis with real-time data, we'd have to do some kind of streaming analysis. And so if we did the same query twice, it wouldn't necessarily return the same results as the data gets updated.
Great. I think carry on. There are a few more questions, but carry on for a bit and then we'll ask some more.
So yeah, jumping back to one of our first projects that Gunnar's going to take us through.
Okay, yeah, I guess the real-time versus streaming data question does come into this. This is a snapshot data analysis, but one thing that we're really interested in, and we haven't gotten to that point yet, but is live updates on these analyses. And we'll show you how that's kind of important in one of these vignettes that we talk about. I'll just mention that when it comes up. But that's sort of like a front end, a new thing that we're trying to get into. All right, so BioRevolutions is a project that we started in Berkeley together in 2014, and we sequentially built up this project and culminated in the capstone in 2015. What we want to show you is our analysis of that. The idea was that, I'll just give you some background on myself. I have a PhD in molecular genetics, and there was a time when I was looking for a job in bioinformatics. When I looked at the domain, I realized how large it was and how varied it was and how hard it would be to predict which of these really exciting projects was going to pan out. I think that's a problem that VCs also have, right? So not only job seekers, but VCs and other people who have vested interest in these biotech companies. So I thought it would be a really great idea to do a more principled analysis of the data and try and figure out what features were most important in these companies. One application that you can sort of nail down and think about is conducting a job search, which was my specific problem. An obvious way to do this is to identify biotechnology hubs, pull positions, and read them. You can do that. You can do something a little bit more nuanced, which is part of our analysis. We pulled 8,000 companies and figured out how many of these actually IPO. The national average was 16% in this data set. We figured out how many scientists are in each of these companies using PubMed data. 21% is the national average. Then if you're interested in digging down a little deeper, like to say if I want to go to San Francisco versus San Diego versus Austin, I can see that these cities really do have very different flavors in terms of likelihood of IPOing. Percent scientists, you can see San Francisco is very skewed in this way. There's a lot of people who are scientists in these companies, but the percent IPO is about average. Austin's kind of the opposite. There's less scientists, but there's more likelihood of IPOing. if you dig even deeper, you can find that this is actually probably not the best place to go. I referred to it before. There's just not that many biotech companies in Austin, and San Diego is a good medium. So this is sort of a traditional analysis. You can take this deeper and do this for every company and figure out what the likelihood of IPOing is using a training set, and then developing a model and predicting likelihood of IPOing for each company that hasn't IPO'd yet. And you can see our distribution of likelihood of IPOs here. Now these are outliers up here, but this guy is the majority of sort of most companies, and 25% is at the very highest range of this cluster right here. So we can see two companies, and I'll take a step back and say this is a snapshot. It's a snapshot from 2013. We've got two companies that look very similar according to our data, which is, again, I want to say it's a traditional non-graph approach to the data. 23andMe today and Theranos today look very different, and we'll argue that graph can get at that difference. The difference between these companies, if you really drill down, is the people in the companies. Theranos has much fewer scientists, and the particular people who are in the company who are scientists are very different than the ones that are in 23andMe. And I don't know if you guys are biologists, but Theranos has been claiming to do a lot of things that they haven't proven, and gotten a lot of trouble, and obviously is not doing as well as 23andMe, which is working on a very principled molecular genetics platform. So an idea of actually just sequencing DNA and making calls based on clinical data and other data that's molecular genetics data. Let's see. So we can use graph to get a little more. And what I'll show you right now is our analysis of a very robust and free and open data set. It's publication data. So these are examples. These publications are examples of years of work on the part of each of the scientists involved. So the title is telling because it's supposed to be the most important sentence in the paper. So we can pull these titles out and put them in a graph and do an NLP on them. The collaboration network is also very important because these authors, most of them put a lot of time into it. Some of them put years into this. So it's a very robust record of real world behavior. There's also where these people were. So there's the institution list. There's the abstract, which is like the title, but a lot longer. So there's a lot of information we can put in a graph and find out real world behavior information. Just an overview. I know we're running low on time, so I'm going to try and run through this. PubMed database has 24 million records like this. 1.5 million of them are easily available and open source. The entire text is open source because they come from an open source journal. So this is what we focused on, and it was enough data to get a really good traction. I know this is going fast, but I don't want to run out of time. I want to show you some interesting stuff. So this is the general schema. You can pull a city out of this. You can pull institutions. You can figure out who the authors are and how they're connected through papers. And then you can get title words and basically see what these papers are about, and then infer what these authors were thinking about and what they're interested in based on that. And it's not just what they've written that they're interested in. It's what they've actually demonstrated investment. And I think that's a really important point. So you can also, so if we just pull the titles by city, we pull the titles by city here, you can do these word clouds. This is sort of the more traditional way to look at this as distributions, but the word clouds have sort of emotional impact. So we put them in here because you can just look at this and get a feeling for what you're looking at. And again, we're falling along the lines of sort of what you might just imagine about these cities. So San Diego has the Salk Institute. Vaccinia virus comes out very strong. And there are very specific diseases that they're looking at here. Similarly, lung cancer. Austin is heavily invested in lung cancer because of the lung cancer journal that comes out of Austin. And then San Francisco is you can see a large number of sort of important and interesting words, but they're all small. And what this indicates to me is that there's a large distribution and exploration across different domain. So just looking at these, you might say, I'm a vaccinia virus, or I'm a virologist, I'm interested in cancer or lung cancer, or I'm interested in like finding out what the bleeding edge is like and taking a lot of risk. Again, stereotypes, but I think the data actually shows this is somewhat true. let's see, quantification. Okay, so the other thing we can get out of this is we can really understand who these researchers are by looking at their publication profile. If you look at the typical publication profile, I've got Colleen Murphy here, who's one of my PI, the primary investigator that I did my postdoc with. You have all of her articles here, titles here, and then words that are oh, these are people. So this is her collaborators. So person-to-person network. A normal collaboration network has the central investigator here and then communities around it. This is Colleen Murphy. This is Scott Emmons. These are two of my mentors. And again, a normal collaboration network has an increase from the number of papers, and then they have more co-authors than papers, more secondary authors than papers, and more tertiary authors. So in sum, we have a linear increase from this to this. Now, we can do this for all the investigators in the database and then look, and we see that there are outliers. Like this guy has way more papers than co-authors, and there's something strange about that. And there's the anomaly. The first question is this guy really a star? It looks like he's got 2,000 papers. That would be incredible. There are people like that. So it turns out he is a star. He won this Jansen Clegg Award, which is a healthcare Nobel Prize. He founded a field called infovalence, looking at Twitter streams and other social media to indicate epidemics. So this is true, but his network is really weird. He has fewer co-authors than papers. We showed you that. You can see the visual impact of this strange network. And what it turns out is actually 1,900 of these links are actually not his papers, so they're misassigned. So there's our outlier detection. And he is an editor, and I think what happened is the editing jobs are called are miscoded as his paper in some cases. So Denis is going to take you through the ecosystem of graph databases.
Yeah, so I'll just rush through these so we can take a couple questions. Next slide. The four graph databases that we've really used are Neo4j, Titan JANUSGRAPH, AGENSGRAPH, and Graken. And Titan JANUSGRAPH is one of the ones that we're just getting into now. The other three we've actually had a chance to use for projects, like the stuff we've shown you. Next slide. So Neo is one of the older ones. It's really helped establish the graph database industry, and Cypher has become the de facto graph database language, and a lot of other databases support it. So Neo4j has done a lot to develop the user base, and with a lot of examples and a ton of marketing. Next slide. Titan morphed into JANUSGRAPH. That's IBM developed Apache project. The great thing about that one is the scalability and being able to distribute it. And it also supports the Tinkerpop stack. And the real benefit of this one is just scalability. Next slide. AGENSGRAPH has the benefit of being Postgres compatible. So if you're not trying to do a full migration, but want to do graph analytics at some point in the future, and you're using something that's either SQL or Postgres, you can substitute this in and then add graph capabilities without sacrificing or having to migrate your existing database. Next slide. And Graken is the one that is really good for really complex ontologies. So as for an example, with Graken, you can connect an edge to a node with another edge. So you have an edge connecting an edge as opposed to just connecting nodes. And so here you can get some really subsets and some really complicated traversals, and it really does a great job there. It really focuses more on hyperdimensional graphs as opposed to just a traditional graph database. Next slide. So here's our contact information if you guys want to get in touch. I'll leave that up and try to answer a couple of the questions. So there's one from Vikram about graph databases and scaling. So SQL and NoSQL database, graph databases are often built on top of NoSQL databases, or at least that's the starting point for a lot of them. They're harder to scale because when you're retrieving data, it's very easy to distribute across rows or distribute across columns, and have multiple databases on the back end serving up, let's say, the rows that you're querying all out in parallel, and then bringing them together for the final results. For a graph database, doing a traversal is a lot more complicated because it's not a linear process, and so those are much harder to scale. And that's one of the reasons why it's really a lot harder to work with that. Titan and some of the other ones are really focused on being able to distribute the backend, but it's not a trivial problem because you have a nonlinear algorithm that you're trying to scale as opposed to a linear algorithm with a relational database. And yes, the question about confidence levels. We do have confidence levels. We didn't dive too much into the analysis for the, I'm assuming you're asking about the BioRes, the original machine learning model. We do have more information on that. We didn't dive too much into it. But if you guys want to send me an email, if you have any questions about that, I can share some more information on what we did there. And there's a couple comments about reasoning systems. One of the great things with, I think is probably a good one for that. If you have relationships between the relationships that you extract from the data, with graph analytics, you're able to do some machine reasoning and deduce new relationships based on combinations of old ones. IBM Watson, if I recall correctly, did a big project on that with analyzing medical research and biology data and then deducing relationships that were not necessarily in the data. And some of the ones that came out, a lot of them were obvious ones that, you know, in the medical industry were kind of common sense. But the fact that the system was able to deduce those, even though they weren't represented in the data directly, was a really good example of machine reasoning.
Yeah, on that, there's a question about AI versus deep learning and how we use graphs for AI. And I think what we're talking more about is the systematically applying algorithms to get answers that we haven't, to dynamically generate questions and answers from the data is how I'm conceptualizing that. It's not that we're applying neural nets to the data yet, but that's certainly something that we would like to do.
Yeah, and graph databases are really good for building up a knowledge graph. When you get into AI and deep learning, you're probably talking more about neural networks, at least for the deep learning part of it, which is usually on more traditional data sets. We've actually done some work on trying to apply machine learning to predicting edges, and so creating a recommender system that predicts edges as opposed to just identifying which ones are already in the data. Thank you guys for coming and joining our talk, and our emails are here. If you have any questions, feel free to reach out to either myself or Gunnar.
Thanks, guys.
Thank you very much, Denis and Gunnar, for the great talk. Huge amounts of interest, getting messages, you know, out of band and in the chat. It's quite amazing. A lot of interest. Thank you.
Yeah, thanks for having us. This was great.
Yeah, if you want to carry on answering questions in the chat for a couple more minutes, that would be fine.
There's a mention of the Google Knowledge Graph. I'm not sure which one I'm opening the link, but I think that the Google Knowledge Graph was used for the Google Jobs API. which is actually kind of interesting because it does some of the things that we built out, obviously without knowing that Google was doing anything with that before they released it. But there's some similar work that they basically use their existing knowledge graph techniques, technology, research, and applied it to their jobs API. And so they built out admittedly a much better version of what we did. I mean, their jobs API that pulls out relationships and does NLP. That's just beyond impressive. Yeah, the Google Knowledge Graph does come up a lot in some of these examples and similar analyses.
And along those lines, I think Benedict, somebody mentioned bio labor. So let's see. So I think I just want to say something that may be interesting to some people. The bio domain is, I think it's ripe for graph analysis because when you're looking at biological data, it's actually a really rich knowledge graph. And there's something called biopacks, which is an attempt using RDF graphs to map all biological data. But I really don't feel like we have a good handle, a good traction on how to use that. Like I've gotten requests to take biopacks and flatten it, right? So people have actually paid me to flatten the graph data, which tells me that it may not be appreciated how valuable these graphs are, right? And maybe it hasn't come to a point where we can really understand how to use it. So this is really exciting to us, is that there's a lot of potential with graphs. It's obviously three-dimensional, right, or more, right, greater dimensions than three maybe. So this is really really cool. I think there's a lot of future for graphs, especially in bio.
Okay, well, thank you again, Denis and Gunnar, and I hope that other people will thank you in the chat as well. It was really great. We all learned a lot. I'm going to close the call now, and maybe see some of you again next week for our next session, which is from someone at Mozilla.
Thank you, guys.
Thank you, everyone.
Thanks, everyone.
Thank you. Bye-bye. Bye.